Welcome to lecture 6.2 over the law of cosines. We just finished in 6.1 the law of sines, so we are now adding more tools to work with triangles, oblique triangles. We'll move forward. Okay, so the section objectives are to use the law of cosines to solve oblique triangles. We're going to look at an application problem, and then we're also going to look at one problem involving Heron's formula. Okay, so as usual, like we learned in the last section, to solve an oblique triangle, that means to find all of its lengths, of its sides, and all of the measurement of the interior angles of a triangle. So we're going to use the law of cosines to look at two different cases, a side angle side and a side 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 case. Okay, so here are the laws of cosine. So we have angles A, B, and C are the measures of the angles of the triangle, and little a, B, and C are the lengths of the sides, just like we had in 6.1. And then we have these equations given to us. So I will show you how this first one is derived here below, and then it would follow the same process for the next two. But basically, what it says is that one side of the triangle squared is always equal to the other two sides of the triangle squared and added, and then you subtract 2 times the other two sides of the triangle times the cosine of the angle opposite the side you're trying to solve for. The square of the side of a triangle equals to the sum of the squares of the two other sides minus, so that's what's stated below. And I'm going to use this diagram down here to explain how the heck we came up with this. And it has to do with the distance formula. Let me just write the distance formula up here, that how we normally see it. We normally see D equals the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, so that's the regular distance formula. Now we need to set up a preface here before we jump into this, and I'll just remind you that the cosine of an angle A is equal to x over b, and that's if we have this triangle set up in this fashion. So let me go back and just talk about this triangle. We have angle A being the angle that is situated at the origin of our plane here. And then, of course, side A is directly across from that. So when I have the cosine of A, I have the value x, which is the adjacent, over B, so this is x, right here. Remember our mnemonic device, SOHCAHTOA. So that says the cosine is the adjacent over the hypotenuse. So in this case, that's x over b. And we're talking about 4 the right triangle, the y side of that being the height of the full oblique triangle. So we can find the cosine of that angle by using that right triangle that's created by dropping the height down from the vertex C. So we have that the cosine of A is equal to x over b, and once I multiply both sides of that equation by b, I end up with x equaling b times the cosine of A. Along those same lines, if I want to know what the sine of A is, well, sine is opposite over hypotenuse. I'm still talking about the sine of A, so the opposite is y over the hypotenuse, which is also b. And when I multiply both sides by b, I get that y is equal to b sine of A. So those two ways of naming the coordinates x, y will come in handy here as we try to see where the heck this law of cosines came from. So we're going to start out with our distance formula, and we're trying to find the length of A. I'm gonna just show you that first one because, like I said, the other two are going to follow the same pattern, and you can go through that on your own if you choose to do so. So A squared, well, A is equal to the square root of, let's see, x, and that's this x right here, the points of that point. So I'm going from this point here to the point C0. So I subtract my x values. That's going to be x minus c squared plus y minus 0 squared. All right, and if I square both sides here to get rid of that square root, because remember, I'm trying to look like A squared equals. So now I have A squared is equal to x minus c squared plus, well, y minus 0 is just y, so that entire last term is just y squared. Now I'm going to use what I've renamed my x and my y coordinates. I'm going to plug those in for x and y into this equation. A squared equals, let me grab my blue pen so you see where it's coming from, b, uh-oh, I grabbed a white one. That's not going to help you see anything. B times the cosine of A, and that's still subtracted by C squared, plus, well, my y coordinate is given by B times the sine of A, and that is also squared. Okay, so I'm not going to show you all the details of multiplying this thing by itself. In other words, squaring it, because I just don't have the room. But it's just algebra, and you know how to multiply a binomial times itself. But once I multiply that binomial by itself, I end up with b squared cosine squared A minus 2bc cosine A plus c squared, and then this last term right here plus b squared sine squared A. And now I'm going to rearrange. Notice I'm trying to get a b squared and a c squared out front. Well, I have my c squared sitting there by itself, so I've got to get a b squared by itself somehow. Well, I have a b squared in this first term and a b squared in this last term. So I'm going to rearrange the terms on the right-hand side so that I can factor that b squared out. So that's b squared cosine squared a plus b squared sine squared a plus c squared, minus, let me delete that. Okay, so it's minus 2bc cosine a. And I factor that b squared out front. Okay, so I'm going to divide a b squared out of those first two terms. And that leaves me with a Pythagorean identity, actually. Cosine squared a plus sine squared a plus c squared minus 2bc cosine a. Well, this Pythagorean identity right here is equal to 1. That whole thing equals 1. So I have b squared times 1. So my final form, a squared equals b squared. That entire first term just turned into b squared because it's b squared times 1 plus c squared minus 2bc cosine a, which is exactly what you see there. And I could go through and do these for the other two, but I will spare you those details. Okay, so when we try to solve a side angle side triangle, we have some steps that we can follow here. So if you're given two sides and an included angle of an oblique triangle, notice none of the three ratios in the laws of sine are going to help you out if you're given a side, an angle, and a side. So that means that you can't solve it using the law of sine. So this is why we have to apply the law of cosines to this. So the first thing you're going to do is apply the law of cosines to find the side opposite the given angle, because you're going to be given an angle, that included angle. And then once you find that, then you'll be able to use the law of sines to find the angle opposite the shorter of the two given sides, which is always an acute angle. And then finally, you'll just use the formula for the sum of the interior angles of triangle to find that third angle. So let's go ahead and work through a problem using these steps. Okay, so the first step, we have a triangle here. We have an included angle A and two sides. So side, angle, side is what we're given here. So our first step is to use the law of cosines to find the side opposite the given angle. Well, the given angle is angle A. So the law of cosines that I want to use is the a squared one, since I'm trying to find the side opposite the given angle. So a squared equals b squared plus c squared minus 2bc cosine of a. So I'm just going to plug in my values and solve. A squared equals 7 squared plus 8 squared minus 2 times 7 times 8 times the cosine of 120 degrees. Make sure your calculator is set in mode degrees, not radians, for this section. All right, continuing to simplify. This is 49 plus 64 minus 112, and then the cosine of 120 is negative 1/2. And when I add all these up, well, multiply those and add everything up, I get that a squared is equal to 169. And to find the actual measurement of that side, I need to take the square root of both sides. And I get that a is equal to positive or negative 13. However, I can discount negative 13 because I'm talking about a length here, and there's no such thing as negative length. So what I found so far is that side A is equal to 13. Moving forward with this problem. Okay, so step 2 says to use the law of sines to find the angle opposite the shorter of the two given sides. Well, I have side B as my shorter side, so I'm going to identify what angle B measures, and I know it's going to be acute because side 7 or side B is the shorter side. So I use the law of sines that will give that to me, and I start out with E over the sine of B equals A over the sine of A. Pardon me. And I'm solving for B, so I'm just going to cross multiply here. And that's A sine of B equals B sine of A. And I'm trying to solve for angle B, so I'm going to divide both sides by A. And I get sine of B is equal to B sine of A over A. So just plugging my values in, I have that the sine of B is equal to 7 times the sine of 120 over 13. And when I put all that into my calculator, I get that the sine of B is approximately 0.4663. And so now I take the inverse sine of 0.4663, and I get that angle B is approximately 28 degrees. Okay, last step. Okay, so let me just mark this. I have 13, and I now know that this is 28 degrees. So all I have left to do to solve this triangle is to figure out what angle C is, and I can use my simple formula for the sum of the interior angles of a triangle that says angle A, I grabbed my white pen again, angle A plus angle B plus angle C is equal to 180 degrees. Angle A is 120 degrees. Angle B is 28 degrees. And 120 plus 128 is 148. And when I subtract 148 from both sides, I get that C is 32 degrees. So that completes everything that I need to say that this triangle is solved. I've got all three sides figured out and all three interior angles. Next, we're going to look at the case of a side-side-side triangle. Okay, so the process for working with a side-side-side triangle is first to use the law of cosines to find the angle opposite the longest side. And that's going to be an obtuse angle if it's opposite the longest side. And then you'll find the two remaining acute angles using the law of sines, and well, you can find just one of the acute angles that way, and then the third one you can use the formula for the sum of the interior angles of the triangle. So we'll take this problem through step by step, just like we did the last one. Okay, so we have the situation here where we have a triangle and we know the lengths of all three sides. So we're wanting to solve for the interior angles of the triangle. So first we're going to use the law of cosines to find the angle opposite, wrong color again, opposite the longest side. That would be angle B. So I'm going to use the version of the law of cosines that gets me to angle B, and that is B squared equals A squared plus C squared minus 2AC times the cosine of B. And this time I'll be solving for the cosine of B instead of solving for the side like I did in the last problem. So I'm just going to go ahead and plug everything in that I know. 10 squared equals 8 squared plus 5 squared minus 2 times 8 times 5 times the cosine of B. So that's 100 equals 64 plus 25 minus 80 times the cosine of B. And that's 100 equals 89 minus 80 times the cosine of B. Subtracting 89 from both sides, I get 11 equals negative 80 times the cosine of B, and dividing negative 80 off of both sides, I get that negative 11/80 equals the cosine of B. So I take the inverse cosine of negative 11/80, and when I put that into my calculator, I get that that is approximately 98 degrees. And that should make sense because when cosine of an angle is negative, that has to live in quadrant 2. Because remember, or quadrant 3, but with this one, we're above the x-axis. We're in the first 180 degrees. So it lives in quadrant 2 because cosine corresponds to the x values. And in quadrant 2, x is negative. So it would make sense that this angle is going to put that into the second quadrant, which it is because it's past 90 degrees. So here's what I've figured out. I have figured out that the obtuse angle here is 98 degrees. Now I'm going to, in my second step, use the law of sines to figure out one of the other acute angles, and then I'll use my formula for the interior angles of a triangle to figure the third. Okay, so we know that angle B is equal to 98 degrees. And I'll go ahead and work with angle A this time. So I'm going to use the law of cosines in the form of B divided by the sine of B equals A divided by the sine of A. Okay, and when I rearrange that to solve for the sine of A, I get the sine of A is equal to A times the sine of B divided by B. And if you're curious as to how I get that, you can just look at the last slide or the last problem where I explained how that works like that. So I have the sine of A equaling A is 8 times the sine of B, which I now know is 98 degrees, over B, which is 10. And when I put all that into my calculator, I get that the sine of A is approximately 0.7922. Pardon me. And when I take the inverse sine of 0.7922, I get that angle A is approximately 52 degrees. So I know this now. That's 52 degrees. And so all I have left is angle C. And I actually have another slide for this, but I've got plenty of room on this slide. So I'll just go ahead and finish this problem off here and change colors since we're on step 3. And I'm going to use the formula for the interior angles of a triangle, which says A plus B plus C equals 180. Angle A is 52 degrees. Angle B is 98 degrees. I'm looking for angle C, and that all has to equal 180 degrees. When I add 52 and 98, I get 150 degrees, plus C is 180. Subtracting 150 from both sides, I get that angle C is 30 degrees. So I've now solved my triangle. Angle C is 30 degrees. So I have a 30-degree angle, a 52-degree angle, and a 98-degree angle with sides 10, 5, and 8. Okay, so we have an application problem here. It says 2 airplanes leave an airport at the same time on different runways. One flies directly north 400 miles per hour. The other airplane flies on a bearing of north 75 degrees east at 350 miles per hour. How far apart will the planes be after 2 hours? So let me describe what you're looking at here in the diagram. I have one plane here, and y'all will get to see how totally awesome my drawing abilities are. There's a plane, and then there's one plane here. And that was dripping with sarcasm, by the way. I do know that I have no artistic ability. My stick figures even look bad. Anyway, they started at point B and took two different routes. We had one that started traveling north and one that started traveling north by east. And the one traveling north went 400 miles per hour for 2 hours. So this side length is actually equal to 800, 2 times 400. And then 2 hours for 350 miles per hour, this side length is 700. So I have a 700, an 800, and I have an included angle. So I have a side angle side given here. Side 800, included angle 75 degrees, side 700. So I'm going to use the law of cosines. The question is, how far apart are these planes after 2 hours? So I'm basically just looking to find what's the distance B. It's across from angle B. So B. So I'm going to use the version of the law of cosines that solves for side B. And that's B squared equals A squared plus C squared minus 2 times AC times the cosine of B. So I'm just going to start plugging things in. B squared equals 700 squared plus 800 squared minus 2 times 700 times 800 times the cosine. Oh, I know B. Let me delete that because I know that B is 75 degrees. So times the cosine of 75 degrees. All right, and then I just start putting all this into my calculator. So I get that B squared is equal to 490,000 plus 640,000 minus, when I multiply all those together, I get 1,120,000 times the cosine of 75. And when I add these numbers out front and subtract 1,120,000 times the cosine of 75, I get that B squared is equal to 840,122.6695. And then I need to come back and take the square root of both sides, and that gives me B is approximately 917. So the planes are 917 miles apart after 2 hours. And that's it. Okay, so this is our last concept, and we'll have one problem to work with this, and then we'll be done with this section. And that's Heron's formula. So approximately 2,000 years ago, the Greek mathematician Heron of Alexandria derived a formula for the area of a triangle in terms of the length of its sides, A, B, and C. And that's how we gained Heron's formula, which says the area of the triangle is equal to S times S minus A times S minus B times S minus C. And what is S? S is 1/2 the perimeter. So we'll see how this is used. All right, so the first thing we want to do is find that value S. And S is equal to 1/2 times the perimeter, which is all of the sides combined. So here S is equal to 1/2 times 6 plus 16 plus 18. So S is equal to 1/2 times 40, which means S is 20. And now I'm ready to use Huron's formula. So the area of the triangle is equal to the square root of S times S minus A times S minus B times S minus C. So in this case, that's 20 times 20 minus 6 times 20 minus 16 times 20 minus 18. And that is 20 times 14 times 4 times 2. And that is the square root of 2240. And that gives me approximately 47. And we're talking about area, and it's given in meters. So it's meters squared is the area of that triangle. And that's all I have for you for 6.2. I'll pick up with 6.3 next week.